put thermal mass where you said thermal mass, and you put insulation where you said insulation, then you would get full credit on the model. You got to meet all the design guidelines, like the 1 square foot of interior floor space, the windows and doors that open, that kind of stuff. Thanks. I need you to put something on the windshield of my Tacoma.
It was open, so I locked it.
Okay. Sorry, children. Side job is interfering with my life for a second. Okay. We had no vocab on assignment 8.2, correct? And there's a couple study goals that I'm going to do out of order. So I'm going to skip, start with number 10. I'm going to skip 10, 11, 12, I believe. And 13 I'll talk about really briefly. We'll start taking notes, I think, on one after. Anybody know the date today?
7.
You can put that on the windshield wiper.
Yeah.
And put the specular. I'm so embarrassed. I didn't transfer money from one account to the one that I'm using to pay the contractors at my mom and dad's house. I wouldn't normally have done that during class time. I bounced a check to our landscaper, and he's a former student. So he's like one of you that went on to like run this really cool, like sustainable landscaping company. I'm like, oh John, it'd be great to have you do this work for us. And so he did all this work for my parents' remodel, and I just bounced his check. That's not cool. Number 10 we'll come back to. Number 11 we'll discuss soon. Number 12 I wanted to speak about really briefly. Does anybody know anything about sports that could bail me out? Who feels like they're kind of knowledgeable about the world of sports? Have you watched sports? Name athletes? No, I mean a sport. Zing. Basketball, football, baseball, any of that? You know somebody? Okay, what's a famous baseball player, basketball player today?
Basketball player?
Yeah.
Steph Curry.
Steph Curry. Excellent. Golden State Warriors? I know a lot about sports. Steph Curry still plans to play next year?
Yeah.
How many years have you been playing?
I want to say like 6 or 7, maybe.
Have his averages been getting better over his career or worse over his career?
Definitely better.
So he plays better and better every year?
I think so, yeah.
Okay.
Well, technically last year they got like the best player in the world, so his numbers went down a little bit, but.
Wow. Okay. Okay. But you would say that by many ways of measuring his performance, it's still better, even though. Okay. Okay. I think it's already been started. So what I'm hearing from you, without knowing any better, I'll just take your word for it, that Stephen Curry, it's not Stephen.
Stephen, yeah, he prefers Stephen.
Stephen Curry is playing better and better every year for the last 5 or 6, even though there's something weird about the numbers that wouldn't maybe make it look that way analytically. You're confident that probably next year his numbers would probably continue to get even better.
Yeah.
All right, all right. Hey children, we just had a conversation with somebody who knows what they're talking about that discusses the long-term trends, the big career averages of a single athlete, Stephen Curry. Were you all listening to the conversation that I had with Davis Kim? Now, Stephen Curry probably misses some shots. If he's bouncing the ball, dribbling, and he goes for a layup, there is no reason to believe that Davis Kim could give you a reliable, dependable prediction before the ball leaves Stephen Curry's hand about whether or not that shot's going to go in, right? Like, he knows a lot about basketball, much more than me. But I don't know. If you just, like, pause right where Stephen Curry's about to let go of the ball, you know, he's better than me. He might say, like, well, he's coming off his bad foot. His chances aren't as good. But who knows? That could go in. Or Davis might say, oh, no. That's his strong approach. There's nobody blocking. I think that's guaranteed to go in. That could still miss. But because Davis Kim knows some of the averages, he'll probably be able to tell us with pretty good reliability that next year Stephen Curry is going to make 65% of his layups. Okay, well, there you go. We're having a climate discussion. Whether or not that one layup goes in is weather. Weather is dependent on a bunch of variables over a short period of time, very difficult to predict, and always has variation. Climate is long-term trends, big averages. Can you imagine? Like, not even I would do this. You see Stephen Curry dribble to the board?
Basket.
Yeah, the basket. What's the thing that the basket's on? Backboard, dribble toward the basket. He goes for the layup. He misses. And Jose says, oh, well, clearly he's a horrible player. He can't be good. He just missed. What's the climate change, global warming metaphor of that situation?
It's raining.
It's cold.
So there's no global warming because it's cold right now. I'm wearing a sweater. How can there be global warming? Man, you would not believe this is a personal pet peeve. Not because I know anything at all about sports, but because I do know a little bit about climate. You would not believe how many times I've stood in a supermarket line or like in the waiting room at the dentist or whatever and heard someone say like, huh, those hippies with their climate change talk. I'm wearing a sweater today. How can I ever go? It snowed in Washington, D.C. today. How can there be global warming? Ridiculous. Check it out. Miss a shot, make a shot. Hot day, cold day. Wow, really good year, really bad year, but long-term averages. You know, maybe Stephen Curry tears a ligament in his knee, has 1 year that's really bad. That would be a big exception in his career, which will probably continue to be distinguished because I'm sure he's a hardworking and talented man. Likewise, we can say some stuff about climate. We can say that, you know, you might get a hot day or a cold day, but on average, you're going to get a lot more really hot days. You can say that climate changes. It changes all the time. But given the records that we know about on our planet, we know that climate changes very, very slowly, and it's been changing very, very quickly. Those things are really, really obvious and clear. The method by which humans change the climate is indisputable. It's basic. You can make little models that work the same way as our atmosphere. We know that climate changes on its own all the time. And we know that recently climate has done something unprecedented. And I gotta warn you about something. I try to be like a level-headed person, and I try to give people the benefit of the doubt, and I'm sure I have all sorts of implicit bias, but I like to think that I can talk to all sorts of people, but this thing about doubt about climate change, that's just silly. That's just silly. I got a couple of days where I'm gonna give you like a really long lecture to clear this all up later, but I wanted to start with that clarification between climate and weather. We'll come back to this later on. Anybody want to ask me anything at this point? Do you like my basketball single layup career averages Stephen Curry metaphor for weather and climate? Does that work? Number 13, I'm guessing everybody can copy out of the book, so I don't need to nitrogen, oxygen, argon, whatever. Okay. We're going to spend a lot of time on number 14. Let me get that diagram. Does everybody have that diagram that has the temperature doing that? Boom, that one. I'd like to point out 6 things that you can see in this image. I'd like to clarify some terminology. There's a lot of important things that will come up later. Today's tough. I got to put all the little details out, and then we're going to start building on those for the next 3 weeks. Today's got a lot of little details. First thing I'd like to point out, and this is the part where I fell over in period 1 trying to point, so I'm going to stay on the left so I can use my good side, but I can't aim very well, so I'll probably break my screens. Okay, I'd like to point out there are distinct layers: troposphere, stratosphere, mesosphere, thermosphere, and you may want to write, just if you're a nerd and you care about these things, there's another one up there called the ionosphere. Ion, I-O-N, O, sphere, ionosphere. I'd also like to point out, between the troposphere and the stratosphere is that dashed line called the tropopause. Between the stratosphere and the mesosphere is the stratopause. Between the mesosphere and the mesopause, thermopause, ionosphere. The pauses are the gaps between the layers. I'd like to give you some perspective. These are in kilometers, so 10 kilometers is about 30,000 feet-ish, 27,000, 26,000. Anybody want to correct me on that? 27,000 feet? Something. What else did I want to point out? Yeah, 30,000 feet. Oh yeah, check this out. If the Earth was the size of this image that's up here surrounded in cobwebs that make me feel very embarrassed about my teaching environment, if the Earth was that size, the atmosphere would be thinner than a millimeter, about half a millimeter. Al Gore's metaphor is that on a Earth the size of a basketball, the atmosphere is a layer of saran wrap. Technically, it's the thick industrial saran wrap, but anyway. The atmosphere's pretty thick. It's a whole lot of dirt, little tiny atmosphere. Those gases are packed right against the dirt. Because, you know, gravity. And inside of that little tiny saran wrap layer, that's where all kinds of crazy stuff happens. All the weather you know about, all the high atmosphere stuff that you don't know about, all that thing about how satellites like make the fireball on their way in, and like all that crap, that's all in that teeny little skin on a basketball. I mean the entire atmosphere is a thick layer of saran wrap on a basketball. This plus the ionosphere, all of that. I'd like you to notice 6 things about this picture. You probably want to write them down because all 6 of them will come up at some point. 6 things about the picture. Thing number 1. Our atmosphere has distinct layers. Like a jawbreaker. Kids your age know what a jawbreaker is? Those still a part of your cultural life? Each of these layers has a different temperature trend. Cools off, heats up, cools off. Cools off, heats up, cools off. Each of those layers has different ingredients. You can breathe in most of one, but there's really no significant amount of oxygen in the others. They have different chemistry because they're exposed to different energy levels. Chemical reactions that happen in the troposphere would not occur in the stratosphere or mesosphere or ionosphere. Each of those layers is a completely unique, different thing. And we're going to say this a lot in my class. We'll talk about tropospheric stuff. Then I'll say, hey, we've moved on to the stratospheric stuff. We won't really talk about chemistry in the other ones because it's pretty complicated. Things are pretty weird up there. Observation number 2. When you look at this image, can you identify visually what the atmosphere's heat source is? What is the hottest part of the atmosphere?
The ground.
The ground. That's really important. Number 2, the ground is the heat source. The hottest air is where the soles of your shoes are. You remember, because you watched the movie yesterday, you know, everybody's had like the black sweater, white sweater conversation. They're both in the same temperature, they're both subjected to the same light, but you know, when you absorb light, then you radiate the heat, and since white is the reflection of all visible light, and black is the absorption of all visible light, the black sweater is warmer, because it absorbs more solar energy and thus radiates greater heat. In the dark, a white sweater and a black sweater are just as warm. They have the same insulation value, but one of them feels warmer because it absorbs light and gives off more heat. Everybody knows this, right? Absorption of light, emission of heat. Number 3. Gases respond to gravity. So something you see here is that most of the atmosphere is pretty low to the ground. You know this Because if you go from sea level to 12,000 feet, you have trouble breathing and you'll get headaches. And if you go from sea level to like 18,000 feet, you can like throw a blood clot trying to breathe and stuff. That's because, ow! Oh, God. That's because gases respond to gravity. So, you know, almost the entire atmosphere is being pinned down on the surface. And as you go further out, the atmosphere gets significantly thinner. Those of you who speak math, it's an exponential curve. So watch this, please. That's 90% of the atmosphere's volume. That's 9% of the atmosphere's volume. From here, almost to the ceiling, is 1% of the atmosphere's volume. If you understand what I mean by exponential growth curves, almost half of the Earth's atmosphere is right there. That's about 50% of the atmosphere. It is worth knowing that gases respond to gravity. So here's an interesting question. Where would you find the most volatile gases? Higher up, because they're able to escape gravity longer. Here's an interesting thing that is not on this that I'd like you to draw on your paper, please. If you made the drawing, there's a reason you did that. There's a spectrum of the laziest gases at the bottom, all the way to the most volatile at the top. If they're lazy, gravity grabs them better. Since most of our atmosphere's gases are lazy, most of the atmosphere is right down there. That's about half our atmosphere in between my two fingers. That's all the lazy stuff. Then the gases become slightly more active, slightly more active, slightly more active, and super, super, super active. The ones up at the outer parts, those are highly, highly, highly active. Observation number 4, ozone is also known as O3. It's 3 oxygens stuck together. And ozone lives in the stratosphere. You can see this concentration thing. Almost all of the ozone is up there. Humans live here on the ground. Clouds are there. Airplanes fly here. And most of the ozone is way above that. I would like you to know that most ozone is centered in the stratosphere. That was observation number 4. When you answered the first question in the movie yesterday, there was something about ultraviolet and ozone. Does anybody remember what you wrote for number 1? Yes? What does?
Ozone.
Okay. So can anybody tell me where you would find more ultraviolet on the flat screen? Higher up. And that's true. If I could somehow dangle your body around here, first of all, it would freeze solid. Second of all, you would suffocate. Third of all, you would fizzle. Like maybe you've seen denture cleaner or Alka-Seltzer in water before? Like a little effervescent bubbling. Your skin would do that, and then most of your meat would do that. Not really sure about your skeleton, but I think probably. Because up here, the part you got to know is heavy concentrations of ultraviolet make most chemical bonds impossible. In the upper atmosphere, it's a crazy environment. Almost all chemical bonds can't hold together. There's so much ultraviolet up there that chemistry doesn't happen the way it does down here. We're living in a very sheltered part of the earth. Because ozone protects us from most of the ultraviolet, our chemistry down here is stable. But because there's hell of ultraviolet up there, chemistry's hell of unstable up there. And observation number 6 before I get out of here. Our planet has a really interesting magical ingredient called water. And we just did the water cycle, and right at the beginning of the water unit, I did that thing where we talked about evaporation, condensation, precipitation, that hopefully you remembered from kindergarten or preschool or something. Now please look up. Because our atmosphere cools as you go up, water really cannot survive as a vapor very high. So water does a really neat trick in our atmosphere. It cools the surface and transfers that heat to the air. Number 6 is we have this magical ingredient called water, and it transfers heat. A simple visual that you all know. I put hot soup, fresh out of the pot, hot soup in a Tupperware. Then I put a lid on it. Compared to an identical Tupperware with no lid, what are the temperatures of those two soups? Which one is hotter? The one with the lid or the one without a lid? The one with the lid, right? Why? How?
Because the water.
Where did the heat go in the one with no lid?
The steam is taking it away because the steam's being blown.
Notice that the steam's ability to depart takes heat away from the soup, and then that steam, even if it condenses somewhere else, will donate heat to something else. You can probably tell, because if you put your hand over the soup, you feel heat on the bottom of your hand, where the steam is bringing that soup. Some of you know that steam can cause burns. Some of you know that steam is dangerous in a kitchen. Because steam, transfers heat from one thing to another. So, number 6, water's magic. It takes heat from the surface of the earth and transfers it to the atmosphere. Water works as a heat exchanger. If you don't have water, the land stays hotter and the atmosphere stays cooler. These are such basic details. I know that you all pretty much knew this already, but I gotta get it all lined up because we're gonna come back to this later. Did I mess anything up? Anybody want to ask me to clarify something that I probably didn't need to say when I said it wrong? Tight. Look up at number 15. Our planet has 6 primary air circulation cells. I'm guessing that you wrote these. Maybe your drawing is not as good as the one on the board. There are a few details that your drawing will need. First of all, the names. They are polar, feral, also known as temperate. Hadley, also known as tropical. And they go in both directions. North Hadley, South Hadley, North Ferrol, South Ferrol, North Polar, South Polar. You have to know all of those terms. I'm sorry that they're used interchangeably. In case you didn't catch that, I wrote them here. North Polar, North Ferrol, or temperate, North Hadley, or tropical, and those names continue south. In case your drawing didn't have that, please look up. You can divide those in 30-degree increments. 0 is the equator, 30 is the gap between Ferrol and Hadley, 60 is the gap between polar and Ferrol, 90 is the center of the polar cells. We're going to talk a lot about these, so I want to make sure that you have that stuff in your drawing. There's a reason I spend a whole day in a crowded unit doing these basics. Ask me if you have questions about what I said so far. Okay. Please look at my hands. Please look at my hands. Imagine that these are gears, or wheels maybe, and that they are touching where they intersect. See what I'm doing? Everybody got this? Gears or wheels?
Pardon the interruption. Boys lacrosse, JV and varsity have a mandatory meeting in room 210 after third period. Again, 210 after third period, varsity, boys and JV in room 210. Thank you.
Okay. Okay. Now watch me. If I've got those two wheels and they have friction between them, if I move my right hand, is that clockwise for you? This is clockwise? Counterclockwise? Okay, watch. If I move this hand counterclockwise, which way is the other hand going to go? Can you see how they move opposite from each other? Watch. I'll spin them in the other direction. Watch my hands. See how they move opposite of each other?
Yeah.
So now please look here. The strongest, the most stable, the most powerful driving force in all of these that will help you remember the directions that you're going to need later is this. The equator gets 12 hours of sunlight every single day, so there's a significant amount of hot air rising from the equator that spins them like this, which pulls the other ones in the opposing direction, which drives the other ones, again, in the opposing direction. I noticed when I was stamping that some of you just kind of drew doodles and some of you didn't have the right arrows, but those arrows matter. You wrote that, sorry. About those cells, our planet has 6. That's just because of how far we are to the sun and how much water's in the atmosphere and because of the size of the planet, and I don't know why it's 6, but you got to know that there's 6, you got to know their names, and you got to know their directions. And next, we're going to talk about how this influences weather and climate. But before we can do that, I'd like to explain what's happening inside of a single cell. And in order to explain that, we need to do 4 basic laws of atmospheric physics. These are really, really, really basic. Technically, they also apply in water. So if you've heard of fluid dynamics, atmospheric dynamics is fluid dynamics. Anybody want to ask me anything before I do the 4 basic laws of the atmosphere? Okay, get ready. Heat is a measure of excitement, and pressure is a measure of collisions between molecules. More heat means more excitement, means more collisions, means more pressure. Please look up. Heat is proportional to pressure because with more energy you get more collisions. Do high school kids go to punk shows very much? How many of you have been to a punk concert? Okay. How many of you have seen rock and roll or punk concerts on television? You know what a mosh pit is? All right. You go to your stupid, tacky concert. You sit there in your black t-shirt. Music hasn't started, and everybody's just kind of like standing around waiting for the music to start. Up near the front, where the sound is the loudest, and you can see the band getting aggro, you start to feel the aggroness, and maybe you start to like move your arms a little bit, jerky, discoordinated, and you start to bump into other people, and you start to push off of each other, and the mosh thing starts to happen. People like kick out their elbows and lift up their knees and push away from each other and push people away from themselves. And as each person's energy level goes up, the number of collisions goes up, you get more contact with other people, the more excited you get. And that mosh pit starts to spread out because there's more people bouncing off each other. How many of you kind of understand this phenomenon through some means, like you've seen it on television or experienced it or heard about it? Okay. More energy in the individual molecules causes more collisions. And now check this out. That material spreads from an area of high pressure to an area of low pressure. Mosh pits expand, and there's more space between them than there is in the quiet shoegazer ones on the side. Like this. All matter goes from high pressure to low pressure. Because, you know, more collisions is more kinetic energy is spreading out. That's what that means. High pressure goes to low pressure. High pressure goes to low pressure. Number 3, that's why we say that hot air rises. I gotta warn you, hot air only rises when there's colder air above. There's this wacky thing that happens in our atmosphere where heat can spread over a mountain range and trap cold air underneath it. And you can see this. Hot air balloons will go through the cold air, and when they reach hotter air, they can't go higher. If a hot air balloon is drifting through the air and runs into a hotter air mass, that thing will sink. Hot air only rises when there's colder air above. If you have colder air below, hot air will sink. It's rare. Because what's the heat source of our atmosphere again? Tell me. That's right, the ground. Thank you for saying that. Since that usually is the case, a balloon which is hot will go from this high pressure zone to all that low pressure coldness. But here's a wacky thought. In the rare cases where our atmosphere is flipped upside down, usually by topography, I'll explain that later. We're going to talk about that because this is bad for air quality. That makes smog. In this rare atmospheric condition, hot air balloons sink. We say that hot air rises because our atmosphere is usually like this. You saw that in the previous image. Next. Remember I told you about that water situation? As water vapor rises, it cools off, and by cooling, it condenses. And remember that in order for water to condense, it has to give its heat to something. That was the special heat transfer of water in our atmosphere. So now, let's look at what happens in one of these cells. I'm gonna, none of this would happen if you didn't have a certain density of air and different temperatures and water volume of our atmosphere. So the distances here are just set by the details of our planet. Thank you. On a different planet, these could be shorter or longer or whatever. On our planet, with the size and the amount of water and the distance to the sun. Okay, watch me. You've got hot, moist air rising off land. As it rises, it cools, condenses, and because it's cooled, it starts to fall. Because a whole bunch of stuff is falling in the same place, you build a stack of air molecules that creates high pressure. Those are pulled over to the low pressure where a bunch of air has left. That's why you feel wind at the surface. Where they smash into each other, you get high pressure because the ones above have run out of energy and they've cooled off, so the ones that are rising smash into them. Like a, what do you call those car collisions where a bunch of cars stack up on each other in the freeway? Pileup, yeah. Pileup right here. You get a pileup of air molecules where the rising air smashes into air that has stopped rising. So you build high pressure. That's what drives the cool air over here to fall. Please look up. We draw these as circles. When we detail a single cell, we often draw it as a square. If anybody's really super dorky, you might consider that neither of those shapes is accurate. If you watch me, please. As it picks up heat and moisture, it kind of goes up angular, sort of like a ramp. And as soon as that heat has been transferred out to space, then it starts to fall, opposing that. Again, in kind of like a curved downward ramp. Behavior of a single cell. Now, if you understand basic laws of the atmosphere, and if you understand why it rains here and why this cold air is dry, so far so good? Yeah? If you understand that it's low pressure on the ground here and high pressure on the ground there, low pressure because all the air has left, high pressure because it's like a pile up where falling air piles up on itself. Are we all good with that? High pressure, low pressure? Left, raining, dry? Yeah? Now, everybody please stand up. Ethan Chow, can you work with Abby and Georgia and Aiden and Chloe to take all those papers off my cabinet number 5 while everybody else please stand on their chairs. take all those papers down from there. Be careful. They're slippery. Pass them over to Georgia. She's going to stack them up next to our portable toilet. Yeah, Georgia, you got this. Amor, can you help out? Yeah, all those boxes, all that stuff. Yeah, try not to crinkle it too much. Georgia, you're a horrible person. Don't crinkle it.
Sorry.
Quit crinkling it.
I've already crinkled.
There we go. Getting it. We're getting it. If you want, you might want to actually stand on the desk itself if it looks stable enough. Careful where you step. Sometimes they fall. All right. Now, silence. Silence. We can fix that, yeah. You should just stuff in there. You got to get around the ballast. Ethan Chow, you're going to have to move, buddy. Thank you. Where? Oh. Outside? I don't know, just lower your head a little bit because I'm going to point a laser at you. Check it out, kids. I put a cabinet in front of this map not thinking that I would need it once a year. This is the one time of the year. This. Have y'all noticed that I used each of my posters once a year? Like, I'll use like once a year. Okay, now. Check it out, check it out, check it out, check it out, check it out. What this is a really cool stitch up of 16,000 satellite images of the Earth during the day without cloud cover. So satellites circling the Earth take photographs of the surface during the daytime, and when they don't have cloud cover, they stitch those together digitally. And they project it into a rectangle. You all realize it's not rectangular. This is a really long line. That's a very short line. With the sphere, everyone understands this? Okay, now check this out. At 0 degrees, which is the equator, there's a band of green. You might know the Amazon, the Heart of Darkness, and Indonesia. Look at 30 degrees north. Well, I'm trying to blind somebody real quick. Okay. If you look at 30 degrees north, look at all those deserts. You can see it from space. And again, at 30 degrees south, desert, desert, desert. There's not a lot of land at 30 degrees south. You know, 60 degrees north, remember I told you the boreal forest where all your lumber comes from? Where all of Europe and Asia's lumber comes from? Remember we talked about that? It rains a lot. They've got a pronounced winter, but the ground doesn't freeze solid, so trees survive. Okay, check that out. Wet zone up there. Silence. And then, here's something that you might be surprised by. At 60 degrees south, there's no land except one of the islands of New Zealand. And if anybody knows anything about New Zealand, that's the one that has all the trees on it. Isn't that the South Island? Anybody know anything about New Zealand? What? Okay, anyway, check it out. The driest parts of the planet are actually the poles. Not only because the water's too cold to live as moisture, but also because there's very, very little precipitation at the poles. So you get dry, wet, dry, wet, dry, wet, dry. If you could sit back down, try to brush the dust off your chairs and your tables. You got this, Akila. Push it a little bit more. You got it, bro. Do it. Can we get a full-size human up there? Do we have any entire humans for this? Ethan Chow's got your back. It has little cables. All right. Here's why our planet has distinct bands of precipitation that you can see from outer space. Rising hot air, because the equator gets 12 hours of sunlight every day. All the days are 12 hours. They are equal. That's why we call it the equator. Given 12 hours of sunlight on the daily, that's a pretty reliable, consistent heat pump. That rising hot air takes moisture with it, which cools, condenses, and falls along the wet band at the equator. So if you're in the Americas, this makes the Amazon basin. If you're in Africa, this makes the Congo basin. And if you're in the Southeast Asian archipelago, this makes Indonesia's rainforests. Now that the air has donated all of its moisture and transferred all of its heat to the atmosphere, it will begin to fall as a band of cold, dry air, which is why the deserts are all at 30 degrees north and 30 degrees south. Also why the deserts are so effing cold at night. That air will either wind travel back toward the equator, or if you're on the uphill side of the pileup, it will overland travel toward the 60s, picking up moisture and heat along the way until it rises into this updraft, dropping the moisture again for the wet band at the 60s. The wind that hits those clouds will spin away, either back toward the desert 30s drop off, or up to the pole where you have the polar deserts. Kind of neat, right? You can see it from space. Like, don't you feel like, oh, that's really our planet? I never knew that about our planet. Like, nobody ever taught me that. I actually had this realization talking in class. I think some kid must have had it. I remember, like, somebody asking a question, me being like, yeah, that! Okay, I got one more for you. I'm going to make a really bad drawing. Don't judge me. I'm going to do it really fast. You could probably replicate this drawing unless you did a really good job on the homework somehow. Okay, here we go. I'm just going to freestyle this thing.
Yeah, the wall. Yeah. Is that supposed to be like England?
Yeah.
Africa.
Oh, that was nothing. Oh, that's not right. What did I just draw? Don't look. Okay. I just put a big scrotum in Europe. Oh, God. It won't let me into heaven. Everywhere I go, there's just scrotums everywhere. Oh, Iceland. Where's Iceland? There's Iceland. Okay, there you go. Ta-da.
What is that?
What?
What is that?
That's the Atlantic. Here is Floridia. There is Brazil. Here is the Ivory Coast, or something. I don't have to know. Lesser compliments, you know. We never know the other countries, do we? How many times have you heard someone say that Africa's a country?
No.
It happens all the time. I get all uppity about that, but I've probably made that mistake too. We don't know geography in this country. That is actually a pretty uniquely American thing. Kids your age, compared to like the globe, really bad at geography. I'm sure some of you are better than others, but anyway. Why don't we bother to teach our kids about the rest of the world?
It's America, dude.
Because America's better? Because it's our stuff anyway? Okay. If you don't have that, make your own, because it's about to get complicated. Who's our stuff? Canada? Waiter. You can never know how nerve-wracking it is to draw for an audience like this. I think I have a judgment complex anyway. This doesn't help at all. Dang, man, that's not bad. Good job, Jose. Thanks, Jose. Yeah, we got this. We got this. We got this. All right. Now, I need to combine this drawing with this drawing, and then we're going to spin the earth. What?
What number is this?
This is all number 15.
Okay.
Hey kids, look! This is north. I have to point with my left arm. I almost. This is north. This is south. And this is a human being standing at about 20 degrees north. Which surface wind does that human feel? It comes out of the, and it's heading to the, for that human, that's a northerly wind moving south, right? Everybody agree with me?
Yes.
Yeah? So, if we're here, there's your surface wind, and if we're here, there's your surface wind. Does everybody see what I just did there? Right? I made my surface winds? We all okay with that? And now, children, let's make Claire Baker my sunshine. If Claire Baker is the sun, does anybody know which coast of the United States sees the sunrise first? It's the opposite of which coast in the United States sees the sun set last. Who sees the sunrise first? That's correct. They see Claire first. And you all realize that the sun's not going anywhere. So, which way does the Earth rotate? That way or this way? First way. Because New York sees the sunrise, right? Then the Mississippi River Basin sees, then Texas, then California. Then it sets on New York, it sets on Texas, it sets on California. Goodbye, sunshine. And we get to the shady side of the planet. Everybody good with that? I'm going to spin the Earth now. I need a volunteer, please. There's the Earth's rotation around its axis, which is where Santa Claus lives. I'm gonna fight the war for Christmas, but I'm gonna focus on the Santa Claus part. Okay. I need a volunteer, 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 volunteer. Come on up here, volunteer.
That desk is way too squeaky. Can we get some WD-40?
Nope.
Okay.
Your discomforts are irrelevant for us. Piece of printer paper, please, Derek. Printer paper on the bottom tray. Might have been easier if I just did that myself.
No, you gotta leave them on.
I grant you that. Yes, you are blinded by the light of our sunshine. Okay. Claire, is it getting creepy?
I think the more you talk about it, yeah.
It's a 2. All right. Watch this, children. Stay right here. Right there. Hold the whole paper. Yeah. And when I say go, you're going to spin the Earth. Which way does the Earth spin?
That one.
Great. So go ahead and spin the Earth. Wonderful. I'm going to do it again in a minute when I say go. Come back to start. Audience, do you remember the surface wind I showed you? Yeah? Watch this. I'll be surface wind. You can kind of see through the paper, like these kids right here can see it. If you look right through the paper, there's the surface wind. I'm going to just trace that surface wind. Okay? I will be the wind pretending that the Earth is not moving. But underneath my pen tip, a more will represent the rotation of the Earth. Everybody ready for this? Ready, set, spin the Earth now. Go. Thank you. You can beat it. Now, hand of applause for more. Yes. Thank you very much. More. Okay. You can see where my pen went. I started right there, and I came off a little bit crooked right there. Can you see all that, where the pen came off? You can see that he was dragging his fingers across, so you can see it's kind of gotten smudged up a little bit. And when you add rotation to the Earth, given those surface winds that we explained earlier, you get this, any old piece of ocean trash that leaves Portugal would quote unquote discover the Americas. As an Italian, I think, Christopher Columbus deserves an award for surviving on a boat for a while. But I don't really know if discovering the Americas is that impressive. Northern Brazil catches all sorts of plastic bags and aluminum cans from Portugal and Spain. We get firewood from that, like a driftwood in the Americas. From Europe. Because of this cool rotation. Now start drawing on your map, please. westerlies come out of the west. Trades are relative to European interests. The southerly trade and the southern westerlies are created by the majority of the water responding to the most stable atmospheric cells on a rotating planet. Because of this, you get ocean currents, the big ones. Much of it is in the trades, the surface currents. The wind moves around that way, so the land moves around that way. That's why you see this line. That's why our jet stream goes like this, because it matches this line. That's our jet stream, which is also the Russian jet stream. All of a sudden, my students are like, holy crap, I got to remember all these arrows? And kind of. At least when you know what planet you're on, you kind of understand what you're talking about. And you can do this entire thing, at least that much. If you remember which coast sees the sun first, and where the red arrow is, and the friction, and the 6 wheels. Yeah?
What do the vertical arrows to the right of the wind circle mean?
That represents surface wind underneath the atmospheric cells. This explains the colonization of the Americas by European interests. This explains why we get like water from Alaska that brings us our nutrient-rich cold water and surf. Whenever there's a storm up in Alaska, we get west swell at Campus Point. This is like the tuna migration. This is pretty much the whole kit and caboodle. This is going to come up when we talk about the El Nino. This is why Japan's nuclear fallout from Fukushima Daiichi was for some people a scary situation on our western coast of the United States. Because Fukushima was over here, and stuff went that way to the California coast, which is not where I just drew it. All right. Check it out. Remember that I told you they're not actually circular, they're more like almond shaped, like the barrel of a wave. If you look really closely, this is like hurricanes and stuff, and like tornadoes. Okie dokie. Let's do one more. This is ball number 15. Anybody want to ask me? Ow! Oh man, just kill me now. Don't turn 40. Die young. Live fast. Die young. Don't turn 40. It is just a humiliating, horrifying experience. Every day is worse than the last. I went to the dentist yesterday, and the guy's like, "We really got to work on this tooth." And I'm like, "Bro, I don't think I'm gonna last much more." So I left. Yeah. Okay. Kind of neat. Ask me any questions about this? No? All right. Number 16 is easy by now, right? What makes the earth warm?
The heat from the sun.
Sunlight.
So let's go to number 17. I'm glad you left room for drawings. Man, I love number 17. see here. There was this guy named Milutin Milenkovic. That's Milenkovic right there. His first name was Milutin. He was a mathematician and astronomer. One of those is about horoscopes and one is about celestial bodies.
Astrology is the
Zodiac?
yeah.
Okay. So, Milutin Milenkovic was an astronomer, mathematician, super nerd. You think you're a nerd? This guy out-nerded you for sure. You don't need to memorize this, but just for context's sake. This guy lived in Serbia, which I've heard is kind of hard living during the 1930s and 40s. Homeboy was like a super dork, and he had extremely sharp pencils and telescopes. And he spent his whole life observing celestial bodies, measuring the distances, and writing them down. Today the thing is over here, and today that thing is over there, and today the thing is over here. It's just like distances down to like 400 significant figures or whatever. And he did this for like 20, 30 years. And he sat there and he looked at all the numbers. He's like, yeah, I'm good at math and I'm a nerd and I understand circles, sine waves. Check out what this guy figured out. Our solar system is irregular. It has 3 irregularities that affect our relationship with the sun. Using primary data, his own measurements of the distances in the sky at night, he worked out math to figure out the timing of these cycles. Now that we have computers and satellites, he was shockingly accurate. He found 3 irregularities that you have to know. Irregularity number 1. The Earth's orbit changes shape a little bit. If you've ever played with a hula hoop, please look up. The Earth's orbit gets a little bit more elliptical and a little bit more circular. On a sine wave that takes 100,000 years. Like this. Dang it, we'll do Milenkovic later. Bye-bye.
I remember this lesson.
It's good stuff, right?
Yeah. I think atmosphere was like my second favorite.
Yes.
I love the nuclear energy.
This is because you are a nerd, and I too am a nerd.
Yeah.
Which is why you're my sunshine, Claire.
Oh.
You're not really.